Vidya Chabra is an assistant professor in the School of Electrical, Computer, and Energy Engineering at Arizona State University. She has a MS degree and PhD in electrical engineering from the University of Minnesota, and her research interests lie in computer-aided design for VLSI systems and primarily revolve around physical design, optimization, and analysis algorithms. Vidya?
I figured there would be some glitch. All right. Thank you. Thanks very much, Ara, for the introduction. And I'm extremely excited to be here and present some of the research that I did. One as a PhD student at University of Minnesota a couple of years ago, and some of the research that my group is doing here at ASU. So the title for today's talk is the role of machine learning in electronic design automation, and I'll dive right in. So electronic design automation, or EDA, is an area that builds algorithms to build chips. And for decades now, chips have been growing in complexity. We started at having tens of transistors on a chip to today having billions, if not trillions of transistors. And while Moore's law has been responsible for this growth in complexity, an unsung hero really has been electronic design automation. And it's enabled us to move away from the manual design of chips by hand to the automatic design analysis and optimization of these large-scale circuits. EDA and Moore's law together have helped sustain the compute and energy demands of several high-performance applications today. However, with the end of Dennard scaling, things have become much harder for Moore's law to sustain. Yes, the number of transistors on the chip have still been growing exponentially, as shown by this orange trajectory here, but the number of useful transistors on the chip that actually contribute to an improvement in performance haven't kept up at the same rate, and that's resulted in this saturation in chip performance that we see in the blue curve. So further, the advent of high compute demanding tasks such as AI have made things a lot more challenging. This picture here shows that since 2012, that was the year AlexNet had its success on the ImageNet dataset, the amount of compute used in training some of these large AI models has been increasing exponentially with a 3.4-month doubling period. So bringing that picture in from my last slide here and aligning the x-axis, even though the y-axis is not the same here, my message here is still quite clear. And the message is that previously Moore's law had a 2-year doubling time, and it was able to assist hardware in keeping pace with some of these software demands. But now, after 2010, there's not only been a slowdown in Moore's law, but there's also been the advent of AI. So if you thought this gap here that was created by the slowdown in Moore's law, which is called the design capability gap, is bad, just look at this gap AI has created. We need hardware that is far beyond today's capabilities to sustain these growing demands that AI puts on today's chips. So that brings me to like a big picture question of the research that we do here at ASU is, can we develop significantly better EDA tools that can both help keep Moore's law afloat and help meet these demands that compute-heavy applications have put on today's chips? So to understand how we can bridge some of those gaps, it's important to use through EDA. It's important to understand some of the challenges EDA puts on the semiconductor IC design industry. And I'll talk about 4 specific challenges today. The first challenge here is the problem of scale, or the problem of N in EDA, when most algorithms that perform, let's say, synthesis, place and route of today's chips, verification, have polynomial time complexity in N, where N is the number of transistors. So larger the number of transistors, slower the runtime of these chips. As a result of slow EDA tools, your time to markets have been increasing. That's challenge number 2. And the third challenge here is that since most EDA tools are heuristic-based, they often trade off speed for accuracy and require tremendous amount of manual intervention to generate that high-quality design with the best PPA that we need, power performance area. And the fourth challenge here is that it's a challenge of cost, and it's not just dollar cost that I'm talking about, but there are costs in terms of risk and expertise that are creating high barriers to entry in chip design. And it's because of these challenges, we see questions like this being asked: has EDA failed to keep up with Moore's law? In fact, with upcoming heterogeneous integration, advanced 2.5D and 3D systems, some of these challenges have only worsened. In particular, this scale problem that's mentioned here is worsened as we have much larger systems to deal with. In fact, as an example, I could say that thermal and power delivery network analysis are two critical challenges that need to be addressed when it comes to such large systems or when it comes to these 2.5D and 3D systems. But EDA tools that perform thermal simulation or power delivery network analysis are computationally very expensive and need to address the scale problem in order to support the design of such large systems. So this is where I believe machine learning can help. It can definitely help us in addressing the scale problem and help us adapt EDA tools to these upcoming technologies such as 2.5D and 3D systems. So on this slide here, I've listed a few stretch goals. And if we do want to get to these stretch goals of, let's say, 24 hours, no human in loop, no power performance area loss compared to traditional chip design methods, machine learning is going to be a very key part of enabling this. So for today's talk, I'm going to talk about ways machine learning can help address a variety of problems in physical design. This is specific, again, to the digital design flow and the ASIC design flow. I'm going to talk about how machine learning can address two particular problems. The first is on thermal analysis, and the second is on power delivery network analysis, which have become increasingly more important when we talk about 2.5D and 3D architectures. So in particular, I'll present how machine learning can help optimize on-chip power delivery networks, how it can help predict IR drop hotspots, temperature hotspots, electromigration hotspots, and of course, I will talk about how machine learning can also help generate data to help train these models in itself or help answer this bigger picture question of where did the data come from. And there's no AI talk that's complete today without the mention of LLMs. We had an entire talk about it just before this from Jason, a fantastic talk. And I'm also going to talk about how LLMs can help assist EDA tools in performing some of these physical design tasks. So all of these components here on the left are research problems that we've addressed, but there are also several engineering efforts that go into creating the infrastructure to support some of these machine learning enabled EDA tool research. And I've listed them here, but I won't be talking about them in the interest of time, but for the sake of completeness, I do have these in my slides and you can take a look at them at your leisure. So let's start off with the first one on how machine learning can help optimize power delivery networks. So to get an idea of how ML can be used, I'm going to explain the problem of power delivery network design. So the goal of power delivery network design is to take voltage from the outside of the chip down to every single transistor on the chip without significant losses or while meeting two constraints. The two constraints here are an IR drop constraint and an electromigration constraint. The IR drop constraint states that the voltage at every transistor must be greater than certain specified limits, while the electromigration constraint states that the current density in every wire that's shown here must be less than certain specified limits. And the voltage drop constraints ensure that the chip operates at a specific frequency, while the electromigration constraints ensure that the chip operates reliably. So there are three specific challenges I want to talk about when it comes to designing an optimized power grid. So, well, it's not that the power delivery network should only meet IR drop and electromigration constraints, but they must also judiciously use wiring resources. What I mean by that is that the power delivery network must be a good citizen and share routing resources with other signal and clock routing that's required on the chip. However, there exists a trade-off that's highlighted here. Power delivery networks that are dense, that use a lot of wiring resources, are very good for IR drop, but they're awful for but are very good for IR drop, but they're awful for congestion. And power delivery networks that use fewer routing resources that are shown here are very bad for IR drop. Why? You have lesser parallelism. Lesser parallelism means higher equivalent resistance, and higher equivalent resistance means higher IR drops, which is not good. In contrast to that, if you use sparser power grids, you're very good for congestion because you're saving enough wiring resources for other aspects of chip design. And if you use dense power grids like this, you're bad for congestion. So whenever you have a trade-off problem that's shown here, you can think of an optimization. But the challenge with any optimization is that it's iterative and expensive in nature. In particular, for the power delivery network problem, an optimization will involve a call to an analysis tool to analyze the IR drop and current density within the power grid. And the challenge here is that this analysis step is extremely slow. This analysis involves solving this large system of linear equations of the form GV is equal to J. And one example that's shown here is that a design which has 12 million nodes, this is about 100,000 logic gates, takes 3 hours of runtime just to solve one simulation of IR drop and electromigration, one simulation of IR drop and current density. So any optimization that calls this under the loop is going to be extremely slow and prohibitive. The last challenge here, before I really come to the ML aspects, I know you're waiting, what's so ML about this, is that conventional power grids are really globally uniform, and they're designed to meet the worst case IR drop, which could possibly be in some particular corner of the chip. So when I say globally uniform, you'll notice that the power grid here has the same pitch or spacing between the wires across the entire chip. So what do I mean by that? If you take a look at the current map and congestion map of this chip that's shown here, the regions which have high current are very local to certain regions that are highlighted in red, and the regions which have low current are very local to certain regions that are highlighted in green. Even with congestion, regions with high congestion are local and regions with low congestion are local. So if you look at these chips that are shown here, the most ideal power grid would be if there's a way we could design this grid where we use high wiring resources or a large number of wiring resources only in those regions that demand it. So if I have a region with high current, I'm going to increase my wiring resources there. And if there are regions with low current, I don't care so much about how much wiring resources I use. So the question this work, which is titled as OpenPDN and listed here, tries to answer is, can we automatically design an optimized power grid that meets these two constraints while using the least number of wiring resources? To automate this problem, we defined what's known as a PDN template. And a PDN template itself is a structured building block of a power grid that fits perfectly into a region of a chip that's shown here. These PDN templates vary in their metal layer density utilization. So this is dense and this is really sparse. And when we create these power delivery network templates, the problem of PDN optimization now maps onto answering which template goes into which region of this chip. And this is a question that machine learning can help answer, because now you're thinking about just mapping a particular region on the chip to a specific class. If you think about it, if in this particular chip we have 36 different regions, it's a 6x6 chip, and we have 3 different templates, the entire solution space is 1e to the over 1.5 e to the 17, which is not possible to exhaustively search. And this is where machine learning can again help us. So in this particular problem, we convert the PDN optimization problem into an image classification problem, where the features or the input features are these current maps and congestion map images. The class that has to be is a template ID for each region. And we use CNNs, which have found immense success in classifying images right since 2012. I can't believe it's been over 12 years. But we use image classification, CNNs to perform image classification and identify one template for every region on the chip. So using this method, we found immense success where we could see that the CNN generated power delivery network could meet the IR drop constraints, and it would also provide significant amount of congestion savings. So this number here shows a percentage of congestion savings, but this percentage might look small in every region, but it actually corresponds to thousands of wiring resources that are saved. And the power grid that this CNN synthesizes is represented by these template IDs that are shown in different regions of the chip. So this tool is open source and it's available for public use on this specific GitHub repository. So that's about optimize. I'm now very briefly going to talk about prediction, generation, and assistance. So we talked about how to optimize on-chip power grids. The next work will talk about how we can predict IR drop in different regions of the chip. So as I mentioned before, performing IR drop analysis involves finding voltages at every node of the power grid, which means we are going to be solving this RC circuit to find the voltage at each and every node of the circuit. And in steady state, if you basically remove all the capacitors from this circuit, solving for IR drop maps onto solving the system of linear equations of the form GV is equal to J. But the challenge here is this system is massive. It has over billions of variables, and inverting this G matrix and computing the voltage is an extremely computationally expensive task. But it's important to do it as it's important to perform this analysis to successfully tape out your chip. Another algorithmically similar simulation is thermal analysis. And thermal analysis involves finding the temperature on different parts of the chip. And conventionally, thermal analysis is performed by solving this second order partial differential equations as shown here. And if you have to solve this using a computer, you perform numerical integration techniques to get rid of the derivative. And numerical integration techniques are also iterative and computationally expensive. Here as well, while this shows a transient analysis, if you perform steady state thermal analysis, it maps onto a very similar system of linear equations of the form GT is equal to P. And this as well has billions of variables. And both these simulations, PDN analysis and thermal analysis, take several hours of runtime on industry scale designs. So while the slide here shows a very equation heavy representation of the two problems that I talked about, here is another representation of the problem, which is more picture based. So if you think about the thermal analysis problem, the problem is taking an input power map and generating an output temperature map. Both these maps or images are correlated, where a region with high power also corresponds to a region with high temperature, or a region with low power also corresponds to a region with low temperature. And it's this kind of correlation that simpler traditional, or may I say more traditional ML models are very good at capturing, such as convolutional neural networks. And that's what we went ahead and did, where we trained this we performed this image to image translation task of thermal analysis by training a unit, which is a model that has found immense success in image segmentation in the ML world, to perform thermal analysis for us. We took hundreds of such data points of power and its corresponding temperature to train this model that's shown over here. And we found that whenever we give it a new power map that the model has not seen before, it was able to accurately give us a temperature map within a few milliseconds. While this slide shows the approach to steady state analysis, the slide here shows an approach to transient analysis. So here, instead of an image to image translation task, it's more of a video to video translation task, where the input is a time varying distribution of power and the output is a time varying distribution of temperature. And we took and we performed this sequence to sequence translation task using these models known as LSTMs, or long short-term memory models. And these have found immense success in capturing time varying distributions in the machine learning world. We trained this model again with hundreds of data points or hundreds of videos that are shown here. And we found that once we give it a power distribution that it has not seen before, it can successfully predict the temperature distribution, time varying temperature distribution that's shown here. And this approach brought down the hours of runtimes on those industry scale designs down to a few milliseconds, with about 95% accuracy, if I do remember correctly. So that was a quick overview of how we can use AI to optimize on-chip power grids, and also how we can use AI to predict thermal hotspots or IR drop hotspots. And both these approaches, the key idea there was mapping the EDA world problem, or the chip design world problem, to machine learning. In the optimization, we did that using power delivery network templates. And in prediction, we did that through image to image translation or video to video translation. So that brings me to my third topic here, which is the topic on generation, or how can we generate power? How can we generate data? Because whenever we talk about, I've used machine learning to train these models to perform optimization or prediction, there's a big picture question that comes in on where did the data come from? So the challenge really is that in the chip design world, data is really hard to come by. And why is it hard to come by? Well, three reasons. The first is technology and design IP. We don't have access to the latest and greatest technology process nodes, or let's say the TSMC 3 nanometer process node, because it's hidden by intellectual property. Or we don't have access to the latest and greatest design architectures or Verilog codes of the NVIDIA GPUs. So that's, again, hidden by IP. So that's one reason why data is so hard to come by. Two is that technology itself is rapidly changing over time. Even if we did release a data set today in the latest technology node with the best possible design architectures, tomorrow that data set is going to be outdated, because technology itself scales so fast, and we're going ahead every 2 years with a new design architecture, or every year with a new design architecture. And the third problem here is that it requires tremendous amount of volunteer effort. So if there was somebody from the industry who did say, hey, I want to help out and release this data set, They have to maintain that data set, and they're not incentivized or to create and maintain that data set for public use. There was one such volunteer effort in 2007 by IBM, who released benchmarks for power delivery networks, and it consists of current maps that are shown on the right here. However, all the IBM benchmarks embody all the challenges that I listed over here. They were released in 2007, updated once in 2008. They represent an old technology node, that's 180 nanometer technology node. They were a little bit unrealistic. This is what a real current map looks like. This is what they released. And they did this primarily to hide their IP. And they were very few in number. There were less than 10 such benchmarks that were released. And when we talk about less than 10, we can't use machine learning applications for this, because with machine learning, we require thousands of such data points to actually perform training. So this was the challenge. To address this challenge, we proposed this work called as BGAN, which the idea is motivated by the success generative adversarial networks of GANs have had in generating synthetic yet realistic looking images of faces that are shown here. And the idea is to generate synthetic yet realistic looking distributions of power or current that are shown here using GANs. So the key challenge is training the GAN. Due to the shortage of real circuit data available, we cannot train this GAN to generate high quality distributions that are shown here. So the idea there was, when we're working with this limited data set, we took inspiration from the machine learning world, and we said we could use transfer learning techniques where we train the model in a source data set that's shown here, and then apply transfer learning techniques to apply it to this specific smaller target data set. So the key idea for the successful application for transfer learning is that the source and target data set must share similar characteristic traits. And for that, we tried to understand what are the characteristic traits of a current map. Well, they have some rectangular blocks here that represent memories of low power. They have some hotspots here in the congested regions, and they have some Manhattan geometries that are shown here that are macro channels. And if you look at this, we found a lot of similarity with urban satellite images that are shown on the left here, where the macros can be represented as building tops. The channels can be represented as Manhattan road networks in urban cities, and the hotspots can be represented as trees. So urban satellite images are widely available, and then we could use urban satellite images to pre-train this GAN, and then we applied transfer learning with a handful of real circuit current maps to update those weights. And we noticed that the GAN could then generate thousands of realistic yet synthetic current maps. And here is an example of 8 such current maps that we got. All those thousands of current maps are released on this BGAN benchmark GitHub repository on this link here. So that's about optimization, prediction, and generation. I'm now going to talk very, very briefly. I have one slide on an effort on EDA tool, on LLMs to serve as EDA tool assistants. So in an effort to drive LLM-aided physical design tasks, we've developed this data set, which consists of prompts and response pairs. And the prompts here are different questions that are all related to a specific open source EDA tool. We couldn't do this using commercial EDA tools due to license agreements, of course. So we've released several 1,500 prompts that are shown here, and the responses are either in the form of text or they're in the form of script. And this data set is particular to the open source physical design tool that is here. And we released this a few months ago, and we have a paper that came out in a recent workshop for this particular data set. And we trained ChatGPT using this data set, and we found that this data set does improve the way ChatGPT generates responses regarding open road. The big picture goal of this work is to lower the barriers to entry on using an EDA tool and make it more accessible to people who are non-expert chip designers. We do have a follow-up on this work where we've actually improved over ChatGPT by using a foundational Llama 3 model, but that work was just submitted to a conference, so we cannot talk too much about it, but I'll be happy to share any information on that once that paper gets in or gets accepted, hopefully, fingers crossed. Okay, so this is the last part of my presentation. I have a few slides on the infrastructure, as I talked about, which you can take a look at your own leisure. So to conclude, over the course of this presentation, I gave 4 examples of how machine learning can help optimize, predict, generate, and assist in different chip design problems. All these 4 examples here have help in addressing some of these challenges that I earlier talked about, the problem of scale, the problem of productivity, and the problem of cost. All of these 4 examples have open source supporting software GitHub repositories. So if you're interested in that, that's definitely available. And I've put the links into the PowerPoint slides. I do I do think that machine learning can help us immensely in the physical design space, and some of the works that I talked about do address some of these challenges in physical design. So I'm going to stop here, and I'm happy to take any questions that you have.
Thank you, Vidya. So I just with the transfer learning, that one really strikes me. If you pick the wrong thing to teach it with, I mean, or how do you even know that it's generating things that are correct? I mean, that's
Right. So I guess correctness is one thing, but its correctness is more like realism, right? So how do we ensure that these power maps that are generated here represent realistic chips? To understand that well, the paper lists a few metrics. We use several metrics to think about that. One are two kinds of metrics. Those one VLSI world metrics where we say, hey, these are the current distributions. Can you tell me what the IR drop hotspots are? Are these within reasonable delta of real world hotspots? Or are these within reasonable differences of the IR drop hotspot that I get from an XYZ industry test case? So that's one kind of metric. But since machine learning has been advancing at this advancing and rapidly, the ML world also has metrics in evaluating the realness of GAN generated images. And some of those metrics are like was the Stein distance or the Earth mover's distance. There are other metrics such as Créchet's inception distance. And these metrics basically they're comparing histograms of the generated images to the real world, real circuit images. And they tell you or how quote unquote real or close these images are compared to your real world data set or your real world circuit data.
okay. Makes sense. It'd be interesting to see if you, for example, fed in, I mean, you tried using satellite images that didn't have Manhattan routing,
Oh, right. Yeah,
yeah,
yeah. So
curved streets, and it throws the results off totally
yeah,
or something.
that's absolutely true, because what happened was we started with just Google satellite images, and we were like, oh, this image has a water body, get rid of it. Oh, this image has too many trees, that's too many hotspots, get rid of it. So there was immense amount of manual effort in curating this urban satellite image set here. The three of us, there were 3 authors on this specific paper, 3 student authors on this specific paper, and we spent a month just looking and labeling images that are going to be suitable for this particular task. So, hey, Las Vegas images are great, or hey, New York images are great, but we can't do something that has a large water body in them, or so on and so forth.
Neil,
Um,
go ahead.
yeah, we do have a question from the audience. What is the difference between your study and NVIDIA's design arithmetic circuits with deep reinforcement learning?
So the study, let me just look at the question because I don't. Designing arithmetic circuits with deep reinforcement learning. So I think this paper is more of a survey paper, or was it more of a I'm not sure what exactly the paper talks about, but based on the title, it seems like they're talking about designing arithmetic circuits, which are going to be adders or multipliers using RL. Here, we're talking about very specific problems that are related to physical design or related to power and thermal analysis, as I talked about. RL in general, we've also implemented a lot of reinforcement learning based timing optimization or logic gate sizing, and also a RL-based floor planner. But what we found with RL in particular is that it's very difficult to scale. RL works very well with small local problems, but not something with a much bigger global problem with much bigger global problems. It's very difficult to scale these techniques to, let's say, 1 million gates in the design.
Okay, thank you. How do you handle the problems of kind of model drift within kind of some of these ML techniques that you're using to kind of do temperature and power prediction?
So when you say model drift, are you referring to inaccuracies that come into picture?
Yeah, or if kind of, I guess if circuit design had a fundamental shift in how it was, like do 3D architectures affect it, right? How your distribution networks come in, right? How do you know if your model's really kind of giving you good results? Assuming if the layout
Right.
stays the same, yes, as we shrink
Correct.
nodes, as we get 3D architectures, how is that going to affect your
Correct.
models?
Correct. So a lot of this work is early ML for EDA work. It's about, I want to say, 5 years ago work. And at that time, supervised learning was what we were working with. So the challenge really with supervised learning is that your model is only going to be as good as the data it was trained on. And the minute you get data that's a little bit different, or let's say there's a shift, we're going from 2.5D, or you're going from a change in the layout, adapting to changes in layout is something that's worked very well for us in the same process technology node. But if you move from process technology nodes from, let's say, 7 nanometer down to 5 nanometer, the current distributions scale significantly. And when the current distribution scale, you want to retrain your model to really be able to predict that scale of temperature, because if not, you're going to have inaccuracy. So if you go from one tech node to another tech node, or you change the way the design is done, 2D chips, monolithic chips to 3D chips, you do need to retrain these machine learning models. There are approaches in some of the papers that I mentioned that use transfer learning for process portability. If you've trained it on an older technology node, you can just fine tune it on the newer technology nodes. You don't need as much of data. And that's another approach that we've explored, and I didn't talk about too much in the interest of time here.
Okay. Just a quick question, on that retraining aspect, how long did it take to kind of train some of these models? Because we're trying to save a bunch of time on iterations, but what are we
Correct.
spending on training time, to
Correct.
get to
So
these millisecond? Yep, go ahead.
yeah, I think it really comes down to if the cost of training is really amortized across the number of inferences you do. And something like a thermal analysis, when let's say you train it for our particular thermal analysis problem that was here. I mentioned hundreds of data points. It's about 800 to 1,000, if I remember correctly. So let's say thousands of data points to train a model that looks like this. This took us about 8 to 10 hours with, I don't remember which GPU it was. I want to say a RTX 3080 Ti GPU in 2021. So that was state of the art back then. So does that 8 hours of time, the question is that 8 hours of time worth it to train this to perform inference on unseen designs? And my answer to that is I would like to think so, because when we do thermal analysis, we're not just doing it one time in the design. When we run optimizations that call thermal analysis engines under the hood, we're doing thermal analysis multiple times. So let's say if we're doing some chiplet aware floor planning, and we need a thermal aware chiplet floor planning, and we need this analysis tool, we need to evaluate various what if configurations. What if I have my chiplets arranged this way? What's the temperature? What if I have my chiplets arranged this way? What's the temperature? And we call these analysis engines under the hood of iterative optimizers, which would mean that we're calling thermal analysis engines at least 100 times or 200 times, depending on how many iterations we do. And in that case, 100 times 3 hours of a ground truth simulation is much better. Is much worse than 100 times a few milliseconds.
Sure. Yeah. Okay. Thank you. I think we have one more question from the audience. Power grids have over 10 billion nodes. How can ML help reduce TAT? I don't know if Arun, you could qualify TAT.
I think it's turnaround time. If that's the case, then I can answer the question.
Sure.
That's right. Yeah. So power grids itself, as you mentioned, have actually billions of nodes that are shown over here. And we've talked about this particular problem from a thermal analysis perspective, where I have an input power map and the output is a temperature map. But what I didn't talk about is the same work also talks about power delivery network analysis, where we have an input power map. We map this entire power delivery network, which has millions of nodes, into an image-based representation. And that image-based representation is representing how dense the power grid is in various regions. We also have a distribution of the different voltage source as an image. And we have these 3 input images that then generates, and then use those 3 input images to generate an output IR drop map, which is very similar to this thermal map that's shown here. So if you refer to this particular paper that's specified here, it goes into the details of that I talked about. And when you map the entire power delivery network problem into this image-to-image translation task, it removes the dependencies on the scale. Basically, if you use conventional EDA tools to perform power delivery network analysis, if you have hundreds of nodes, your runtime could be X, but if you have billions of nodes, your runtime is much, much larger than X. But when you map it into this image-to-image translation task, you're not dependent on the scale of the power grid anymore,
Sure.
but you're just dependent on how these machine learning models train.
Okay. When does this training and image generation take into account multiple power domains?
This particular work did not account for multiple power domains. We are working on an extension as we speak on considering multiple power domains. So yes, so look out for that. Yeah.
Okay. Yes. Thank you. I think we've got all the questions.
Yep. I would like to thank our sponsors once again, ASC and Amcor. And with that, I will wish everybody a great rest of their day and look forward to seeing you at a future MEPTEC event. Thank you for joining us.